let's just jump right into it. Today, we're unpacking a reality that honestly keeps IT directors and sysadmins up at night. I'm talking about the intense stress of managing modern, AI-heavy IT infrastructure. Look, if you've been anywhere near high-performance computing lately, you already know that the sheer power of AI brings a massive, frankly, headache-inducing infrastructure challenge with it. We're moving way past standard server racks into these incredibly dense, power-hungry, liquid-cooled environments. And the old ways of managing this stuff, yeah, they literally just don't work anymore. We absolutely have to figure out a way to go from absolute chaos to complete control. So let's dive into this explainer and see exactly how to do that. I mean, we've all been there, right? That feeling of total panic when you have absolutely zero data center observability. Just picture it. You walk onto the floor or you crack open your laptop and bam, you're hit with multiple critical error alerts across all your different infrastructure domains. But here's the absolute worst part. You have no centralized system to actually figure out the root cause. You are just staring at a literal sea of red flashing lights. When you don't have unified observability, diagnosing issues takes forever. And that means extended downtime for your critical systems, which, let's be real, grinds your business operations to an absolute halt. And the thing is, these problems basically never happen in isolation. You aren't just putting out one fire. You're dealing with a full-on chain reaction. It usually goes something like this. First, a power distribution unit, a PDU, trips, and suddenly you've got power issues. Then, maybe a cooling distribution unit fails, which completely stops the flow of chilled liquid to your racks. And then suddenly, your servers are overheating and screaming with critical hardware alerts. It's a domino effect. These issues compound so rapidly. If cooling goes down, server failures are right behind it. If you can't see the entire picture all at once, you're always going to be one step behind the disaster. Okay, deep breath. Let's talk about the solution to all this chaos. Enter the Supermicro Software Suite. Now, the core architectural philosophy here is absolutely crucial to understand. It is modular by design, meaning it is independent but integrated. What that actually means for you is that you get this incredibly flexible software stack where you only deploy the exact capabilities you need on day one. You don't have to rip and replace your whole management framework. And no one wants to be locked into single platform dependencies across all their services, right? This gives you that ultimate flexibility while really dialing down your operational and security risks. So let's quickly map out this suite so we don't just drown in acronym soup. There are 4 distinct modules here, and every single one of them drives serious enterprise value. First up is SuperCloud Composer, or SCC, which is going to be our main focus today. It handles your unified observability, telemetry, and policy-driven monitoring. Next, you have the SuperCloud Automation Center, which takes care of infrastructure automation and provisioning. Then there's SuperCloud Director for managing multi-tenant bare metal services. And lastly, the SuperCloud Developer Console, which is specifically built to handle fractional GPUs in AI environments. The beauty is, you can run these completely independently based on whatever your immediate priorities are. But what's really fascinating is how these pieces fit together. When you use the full stack, the integration is just incredibly tight. Sure, you can deploy them on their own, like maybe you just need SCC for monitoring right now. But when you stack them up, they communicate so seamlessly. It creates this fluid pipeline, right? From monitoring the bare metal hardware, to provisioning the infrastructure, to deploying those bare metal services, all the way up to allocating specific GPU workloads directly to your developers. It is essentially a fully cohesive AI cloud stack, but built entirely from highly modular pieces. Now, to truly grasp what makes SuperCloud Composer so powerful, we really need to talk about a core concept it relies on, and that is RackScale. Basically, RackScale means you are modeling and managing your infrastructure at the physical rack level, instead of just staring at a massive flat list of hundreds of individual servers. Think of it like managing an entire neighborhood, rather than just inspecting the plumbing of a single house. If one house has bad water pressure, okay, that's an isolated issue. But if the whole neighborhood has low water pressure, now you've got a municipal problem. Having that rack-scale context gives you that zoomed-out critical intelligence. So why is this so absolutely crucial for AI workloads in particular? Well, because AI systems have massive, frankly unprecedented dependencies on power and cooling. We're talking pulling upwards of 100 kilowatts per rack in some cases. That is way more than traditional servers. RackScale is a perfect fit here because it lets SCC map and correlate those power and cooling metrics to specific physical racks. This totally transforms your alerts. Instead of just getting a generic alert that says server X is running hot, RackScale context says, hey, multiple systems in rack Y are overheating right now because the specific cooling distribution unit attached to them is failing. And that means you can actually take emergency action on those specific groups of racks based on their physical dependencies. Seriously, just think about high-density AI rack infrastructure. The power density we're dealing with today is just staggering. If a leak is detected in the cooling system attached to a specific cluster, you literally do not have the time to sit there manually hunting down individual server IPs to graciously shut them off. No way. You need a system that intrinsically understands the physical layout. You need something that can facilitate immediate emergency actions, like instantly shutting down that leaky cooling unit and all its associated servers before you suffer catastrophic, expensive hardware damage. Now, to actually pull off this level of advanced rack management, SCC has to communicate with the hardware in a fundamentally different way than older tools do. Legacy management methods, things like IPMI and SNMP, they're just less suited for secure, modern systems management at this kind of unbelievable scale. Instead, SCC is built entirely on the Redfish API, and this is a massive upgrade. Redfish is a secure, completely open industry standard that's based on REST and HTTPS. What that gives you is a consistent, vendor-neutral way to collect system health, power, thermal, and firmware data across tons of different product types. It is literally the rock-solid foundation that makes true rack-level operational control possible. But here's a great question. How does SCC itself manage to stay online when your data center is having a crisis? Well, SCC actually runs on Kubernetes as its underlying platform layer. So it runs its own internal services in a highly resilient, scalable way. Thanks to this modular architecture, its services run as separate components. So if one internal service happens to fail, Kubernetes just automatically restarts it. It's basically self-healing. Plus, it supports high availability with a multi-node control plane, meaning you aren't betting your entire management framework on a single server. And it allows for controlled, structured upgrades, which is infinitely better than trying to patch some giant, clunky monolithic application. Long story short, your management system stays online when you need it the most. And because it's built on Kubernetes, scaling out your SCC deployment is a very structured, logical process. It's not a one-size-fits-all deal. You might start off with a smaller initial proof of concept just to test the waters, but when you move to full production, you step up to a high-availability control plane, which requires 3 separate nodes, whether those are virtual or physical, just to ensure the system never ever goes down. Finally, as your environment grows and you've suddenly got thousands of GPUs pumping out telemetry data, you just add worker nodes. These worker nodes take on the heavy lifting for background jobs and massive data processing, which keeps the pressure off the control plane and totally prevents those dreaded management blackouts. Okay, so here is a really crucial point about how SCC actually gathers all this data. It relies heavily on out-of-band telemetry. Why does that matter? Because it means your visibility remains fully active even if the host operating system completely crashes. Because SCC is pulling data directly from the baseboard management controller, the BMC, it doesn't even need an OS agent running on the workload itself. It captures all that vital server hardware health, thermal data, and event logging completely independently of whatever might be freezing or failing over on the application side. When you start bringing all these pieces together, you get this incredibly rich, unified picture across your entire data center. SCC collects all the asset metadata, so you know exactly what is deployed and exactly where it is. Then it layers in that out-of-band data with in-band telemetry using exporters. This means it's pulling incredibly granular metrics straight from your NVIDIA or AMD GPUs. Add to that its broad integration with smart PDUs from vendors like Schneider and Servertech, and you've got total rack-level power visibility. Finally, it pulls in all those critical cooling metrics, supply temps, return temps, and actual physical leak detection, all of this organized perfectly into one centralized dashboard. But look, observability is only half the battle, right? Knowing about a fire doesn't put it out. And that's where SCC's policy-driven automated actions come in. It doesn't just sit there watching your data center burn. It takes immediate action. If it detects a coolant leak, it can automatically shut down the affected systems. It can completely disable smart PDU outlets to isolate damaged equipment. If a server is hitting a critical over-temperature condition, SCC can actually trigger a graceful shutdown before the expensive silicon literally melts. Or it can just automatically power cycle faulty nodes. It effectively turns passive monitoring into an active, highly intelligent defense system for your infrastructure. Which really leaves us with one final and frankly very important question to think about. Is your AI infrastructure managing you, or are you actually managing it? As these massive AI workloads continue to push the absolute physical limits of power, cooling, and hardware density, those old reactive legacy tools, they just aren't going to cut it anymore. Moving from a reactive state of pure chaos into a proactive state of control requires contextual, RackScale observability, and most importantly, automated defense. So take a look at how your current operations stack up and ask yourself if it's finally time to bring true control back to your data center.